Hello, my name is Liang. This is my workshop 3 video. The paper I'm presenting today is automating the generation of 3D multiple path layout design using BIM and heuristic search methods. The paper was originally presented on 18th International Conference on Computing in Civil and Building Engineering in 2020 and published in the book of the conference the same year. Description of the problem. The piping is a system of pipes used to convey fluid from one location to another. The layout design and the spatial coordination of multiple pipe system is a major challenge in the construction industry. The design of pipe system layout need to consider factors such as building space geometry, system requirement, design code specifications, and the location and the configuration of relevant equipment. The purpose of multiple pipe layout design is to find out an optimal layout, efficient, economic, coordinated between many individual pipes to route from a different start location to the different end location in a 3D environment, and with no clash under all kinds of constraints. Why pipe system layout design is important? Firstly, pipe layout is very popular and play an essential part in our daily life, like in electrical power plant, chemical plants, factory, building, sewage, automobiles. Almost every structure you have seen in your life somehow involved piping design. And its contribution to the overall capital cost is often huge. Pipe layout design is one of the most time-consuming, expensive, and complicated steps in any pipe system design, since it can take over 50% of total design man-hour, and all other detailed design depends on it. This is some background information. I have been working in building design and the construction industry for many years before I came to this master program in computer science. I was not the engineer doing the piping layout myself, but I had a lot of coordination with MEP engineers and had seen them struggling with piping layout, always testing better routes and changing every hour to fulfill the other disciplines' design changes. It's actually one of my future career goals to develop the program, software, or algorithm to improve efficiency in civil and construction industry. So this is a little bit my background and why I'm interested in this topic. The constraints. Firstly, physical constraint. This is the most important one. The pipes need to avoid the clash with structural and architectural elements and other obstacles around, and the clearance for entry and exit requirements. There are many functional or aesthetic elements need to be seen. The piping system is kind of behind the scenes elements. Mostly piping need to coordinate with those physical constraints. Design constraints. This refers to the coordination between the pipes, the clash branching of pipes, minimal equipment clearance, buffer for the danger zones, accessibility for valves and accessories. Economic constraint. This one is invisible, but also important. The total cost could be reduced by minimum pipe lengths and bends. Installation cost refer to how far the pipe location to wall and obstacle for the support accessory. If you can support sharing among pipes, it will also reduce the cost. This diagram shows multiple pipe system. Basically, it's a 3D graph with multiple nodes. which are PEP, starting, end, and the possible bend points. Edges are potential PEP routes. Walkable and non-walkable paths reflect physical and design constraints. You see this one from the blue dots begin to the bend points, the next node, next one, and the end points here. Previous solutions. Conventionally, engineers design the PEP route manually or use physical model. You can imagine this requires huge time and cost with low accuracy. The use of computer-aided design, CAD, software has partially automated the manual process, but they still require human effort and decision-making to resolve the design constraint. And it's hard to make the revision. Also, different design aspects typically require different software, and the process is usually not well integrated. Physical PEP layout design is a complex spatial geometry problem, so there might be several solutions possible, and checking each solution will be NP hard. So heuristic optimal layout technique is very necessary here. So this image shows the traditional CAD design software. You can only see this PEP layout. You couldn't see any relations with the other building structural or architectural elements. The latest on PEP layout is BIM, stands for Building Information Modeling. It's a 3D modeling system integrated with architecture, structure, and all other disciplines. 3D BIM model enable the designer to visualize the geometry of the space, location of the building components, location of the equipment, where all these physical constraints located. And you can see the start and end point of PEP system. BIM somehow support automatic PEP design process, but still it lacks in clash detection and clash avoidance. It just generates a route without calculation of physical constraint. And of course, the PEP routes suggested by BIM cannot guarantee to be optimal paths. So the goal of this new approach in this paper is finding a complete automated and integrated and optimal solutions. So this paper processes a BIM-based approach for layout design of multiple PEP using heuristic search method. Algorithms are derived based on a directive weighted 3D graph. The weight of the path considered to be the regular pressure loss costs along the PEP and installation costs of the system. Clashes between PEP and the with building component are considered and avoided in the layout optimization. For individual paths, Dijkstra algorithm and the two heuristic algorithm, which is a 3D stars and fruit fly, are implemented, and the overall costs are compared between these three algorithms for individual PEP route. Then simulated annealing SA is used for global optimum. So this diagram shows the author's overall approach for layout design. First step, BIM model is not our computer science scope. So I'll start with space and constraint modeling, then move to the fitness function, then optimization for individual PAP. The paper presented 3 algorithms for individual PAP layout, but in this presentation, I'll only present 3D A stars. For global optimum, the study used simulated annealing. Space and constraint modeling. Use directed weighted 3D graph with node and edge. Node is possible junction or 3D point. Edge is segment running between 2 nodes. For economic constraints, minimal length, light spans rotate around the building elements for necessary support and close enough to share common PAP supports, racks, and hangers during installations. For physical constraints, clash with the building architecture and structural elements and other equipment and objects within the defined building space are exempt. The nodes which intersect with various physical components are restricted for the PAP routes and are regarded as unworkable for PAP layout. So look at this diagram. These are 2 common clash conditions for one node, node I. This one is clash with the structural beams. This one is clash between the PAPs. So if node I plus 1 is restricted, edge node I and node I plus 1 is not workable. Fitness function. To calculate the cost due to pressure lost, CP, the friction along the PAP length is calculated as per the total distance traveled by the edge from the supply point to the demand point. Firstly, this formulation calculates the distance between any 2 nodes. Because the bend of the PAP are always 90 degrees, the diagonal PAP layout are not encouraged in the PAP design. And they use Manhattan method. The formulation is showed here. So between 2 node I and node I plus 1, the coordinates is xi, yi, zi, xi plus 1, yi plus 1, and zi plus 1. The distance between these 2 nodes will be like this. X xi minus xi plus 1, which is absolute value, and the y coordinate and z coordinate. This is distance between any 2 nodes. To calculate the cost function CP for one route from the start to next node to the end node, the formulation is like this. CP is cost for N1 all the way to N. The unit is US dollar. CM is material cost for unit length, US dollar per meter. And this one, N is the total nodes. So I is running from 1 to N. Calculate the distance like this one. So this will be the total travel distance in meter. This one, J is the bends. J from 1 to X is the total bends. NBJ is the equivalent length for a bend in meter. In this paper, because the 90-degree curve elbow is considered, so NBJ equal to 30. Frankly, I'm not quite sure why 90-degree bend equal to 30 meter, but this is what this study used. Installation cost, CI. Calculate the installation cost depend on the location of PAP system route. Generally, the distance between the PAP system with a supporting component to hold it is shorter, the installation cost is less. The total installation cost of PEP system is evaluated as per the perpendicular distance of PEP route nodes from the nearest supporting elements, like the walls, columns, or beams. If you look at this diagram, the node A's perpendicular distance to these columns will be this dA. Node B to this wall is dB. This is just from the top view, you can see. So the shorter this distance, the less the installation cost, because the supporting accessory will be less. In this formulation, CI is installation cost of PEP system in US dollar. IC is installation cost of PEP for unit length, US dollar per meter. This one is total N nodes from 1 to N, the total. DI is perpendicular distance of node from nearest supporting element in meter. Sorry, I think I missed one. Okay. Now calculate the minimal total cost is adopted to be the optimal multiple PEP system layout, which is CP plus AI, the two formula we just talked about. Next one, optimization algorithm. The first one is Dijkstra algorithm. I'll not talk about it because we have learned it in the class already. The next individual PEP route optimization is 3D A star. A star is a searching algorithm used to find the shortest path between an initial and a final point. It's kind of an extension of Dijkstra's shortest path. The difference is Dijkstra is based on only the distance to the initial points. A star consider the initial point and estimate distance to the final points. It uses a heuristic function to provide additional information regarding how far away from the goal node. We'll look at in detail shortly. And this paper modified the original A star to a 3D version called 3D A star because of this 3D spatial system. The basic function of 3D A stars here, Fn is final cost, Gn is distance from the starting point, follow the path we generated to get here. This is the same with Dijkstra algorithm. Hn is an estimation of the distance to the endpoint. This is a heuristic function. To calculate this heuristic function, Hn, the 3D space is converted to weighted graph. The nodes which are available for pass is marked as walkable, and the nodes which are not available for the pass is marked unwalkable. Like I mentioned before, this study considered PEP route in the straight direction along the coordinate axis. During each search iteration step in the 3D environment, there are 6 possible movement directions, 2 in x-axis, 2 in y, and 2 in z. Like this diagram shows, if this red node is a current node, there are 6 neighboring nodes which are potential moving direction. These 2 in dotted line marked as unworkable because of some physical constraint. Maybe there's a column or wall or any easement there. The other 4 are potential solutions. The algorithm will choose the lowest cost one to move to the next node from these 4. So the path founding began with the start node and moved to the next workable neighbor nodes next to it, and the next one until the end of node is reached. The cost function of the path we just discussed as a fitness function, the heuristic cost function is this one, HN equal to xc minus xt plus yc minus yt plus zc minus zt. Again, in this study, the Manhattan method is used to determine the heuristic cost function because this is a standard heuristic method of a square graph. The paper discussed another algorithm called fruit fly, FOA, for individual PEP layout, but I'm not gonna show it here in this presentation. Because of finding an optimal individual PEP route does not guarantee optimal multiple PEP system layout for the whole 3D PEP system. So even each one is optimal individually, but doesn't mean the combination of them is optimal. So the study used a meta-heuristic algorithm named simulated annealing, SA, to combine with the single route algorithm to obtain the optimal layout for the multiple PEP systems. SA is a probabilistic technical for approximating the global optimum of given objective function. It's basically composed of two processes: generate a solution and compare them and accept the solution. Firstly, SA generate a random solution and calculate the cost using the fitness function. Then, which is the 3D A star we just mentioned. Then they generate the next new neighboring solution and calculate the cost with the same process. Then it's compare these two solutions. If the better solution is found, the algorithm will accept the better solution and mark as current solution. Otherwise, if the better solution cannot be decided, then we'll use this probability function to determine which one will be the accept solution. The paper doesn't explain this formula in detail, but generally SA is inspired by annealing metal. The metal is heated to a high temperature quickly, then cooled slowly. The acceptance criteria of the ore solution depend on the difference between the two solutions and the temperature parameter. So this is a kind of temperature parameter. As ore solutions are more likely to get accepted at high temperature, the process continues until the termination criteria is met and the final temperature is reached. Well, we don't need to understand this formula here, but the whole process for the simulated annealing is shown like this. Now I will show an illustrative example using this combination of algorithm 3D A star and SA. This one is a typical water plant room model built in BIM software. The architecture and structure elements like the walls, the columns, and beams are all showed here, and the the opening of the wall. These elements all consider as physical constraint for the PEPs. This table translates this physical constraint into coordinate value information. There's a minimal coordinate value and there's a maximum. So all the beam A is between this point and this point. So, and it's a box for sure. So this information shows the blackout point. The PEP cannot go this place. This table shows total of 9 routes to plane for the whole PEP system, and supply points and the demand point reflect to the initial nodes and the end nodes of the path. This side is the output of the 9 routes using the algorithm 3D A star, then SA for the global optimization. This is a overall developer approach diagram for the multiple routing layout optimization. Briefly start initialization of SA parameter, choose initial PEP route combination. So this is the first option. Then PEP route optimization using 3D A star, FOA, or Dextra. The new random PEP route combinations, then calculating the cost using the same way. Then compare these two, accept new cost. If yes, satisfy metropolis criterion. Yes, go to revise as a parameter. If don't accept new cost, no, satisfy metropolis criterion, then go to revise. Is this termination? If no, go to another circle. If yes, then stop. The whole thing is a temperature cycle. This blue one is metropolis cycle. This slide is a comparison between 3D A star and Dijkstra algorithm. The horizontal is the different iterations. Vertical is the total cost. Lower line is the minimal cost. Top line is the max cost. So this 4 different diagram shows 4 possibility or consistor to know how cost is compressed with time. The heuristic cost function used in 3D A star algorithm was multiplied by factor 10,000, 1,101. The higher the factor value, the lesser the time to run the algorithm. This one is Dijkstra algorithm. I didn't include the FOA one in this one because we're not focused on that. So after comparing the algorithm result, it was found that 3D A star with SA with the factor of 1 heuristic cost has the lowest cost, 644,450, which is the same with Dijkstra cost. But this one, the running time is just about 50% less than Dextra. So this one looks like it's the best result with minimal total cost and minimal time spent. This is conclusion from the paper. With adoption of this framework, time and human effort for the optimized pipe system design are significantly reduced. The developed framework can also be used in designing of other trades, such as mechanical, with further modifications. Therefore, extending the framework for other trades will be considered in the future work. This is a reference for the paper. This is my presentation. Thanks. If you have any question, just feel free to contact me. That's it.